Okay, my other story actually has to deal with looking at the data from the 4-year Kepler mission, and it's called Planners Hunters X. Where's the flux? And I'll let you know where that name actually came from. But Kepler has a whole bunch of data, and they keep coming up with better ways to process that data to squeeze out more and more planets. But sometimes computers aren't as good as the good old human eye. So an organization called the Zoo Universe Project here created this website for citizen science. It's called Planet Hunters, where you can go in and start classifying various objects from the Kepler data. So they would say, okay, look at this, and you could see things in the eye that were missed in previous studies. And so one particular object kept coming up in these studies here, and this fancy name here, KIC 8462852, where it had a very weird, unusual kind of transit type features. And so this paper came out in September talking about what could actually cause this. So they did some more depth analysis of this data. And here is the data that is very, very strange. So they have 4 years of data. So they have 1,500 days of data. These are just kind of a montage of the same data set that you see up here. Here's kind of almost drawn to scale. 1 here, of course 0 would be down over here, and you can see a couple dips in brightness here. You see this big one, you see this one, and this one, and this one. Here it would blow that up a little bit. You can see those a little bit better. If you look at in detail of that depth and brightness, there it is. There, nice symmetric profile. This one over here blown up here is even deeper, but look at the depth of that. Again, 20% of this star is now being covered. Now we're not talking a white dwarf, we're talking a flow-blown F star here in this case here. So what is causing that? There doesn't appear to be much periodicity in any of this. So there could be a period that is on the order of, was this 850 days or something like that between that. But that's the extent of that data set. So very interesting results from this. If you do that FOIA analysis that I was talking about before, you don't get a lot of, you get information here, but it's not a transit. You see that spike here at 1, and then these are actually at harmonics. This is in cycles per day, so 1 over that gives you the days, but basically that represents a period of 0.85 days. That actually represents the oscillation of the rotation of the star. So here's another thing that Kepler can do, is that it can see the rotation rate of this particular star. So they were trying to figure out, okay, what is going on with this system? So they went out and took some pictures of it. Here's an image taken from the IRTF telescope. I said the Euclid telescope, the telescope up on Mauna Kea, where you got a picture of it here, and there's a nearby star there. And you can see there's kind of a little blob on the side there. It doesn't look like this same star of a similar type brightness. So they had to then get out the adaptive optics so that they could see even better resolution. And when they resolved that area, here's the image they got. And so they found it indeed had a companion star that was separated at about 2 arc seconds from this star. But it was about a factor of 20 times fainter than this primary star. Then they took the spectra of that star, and they found that star looks to be an F-like star. Nothing peculiar about it in the least. Very unremarkable in terms of it as a star. So what is causing these things? So so they started to look at, okay, what could cause this dipping in the spectrum? One of the things that they looked at was, could it have been the bad data? Could have been instrumental effects. They looked at in really close detail and determined that could not be. This is real data. There is something happening at the source of this particular object. They also even looked further into the data to see if there's any other objects that were like this one. Of the 150,000 stars, there is not another object that behaves like this. Okay, so that was very interesting. And then Intrinsic variability. Is the star itself, could it have that kind of variability? Everything suggests that it is not. They've looked up for other binary companions. They've done radial velocity studies. There's nothing happening with this star to suggest that it would have that kind of variability. Extrinsic, in other words, that other star, companion star that we do know about it, could that have caused that variability? It's way too faint. It could not cause that. So the one potential explanation is occultation by clumps of dust. And where are those clumps of dust coming from? Well, we just talked about a scenario of planetesimals falling apart. So could we have those? But now we're looking for much bigger clouds of gas and dust, right? Because we've got a big star. And we have to be in the kind of the right line of sight. So there's got to be a lot of those around. So there are certain things, no matter what scenario that you have to look at, what's in the data is how long do the dips last? How deep do they go? This light curve gradient, how fast do they rise or fall when they go into one of these dips? The fact that we're not seeing much in terms of periodicity, at least yet. And, if these are clumps of gas and dust, they've got to be gravitation bound, or how are they not dissipating by now? And then something called infrared excess, which is actually the major player here. They took a spectrum of this star here, and here's the spectrum of an F-like star. If these are clumps of gas and dust, we should see an excess of infrared emission out over here, and we are not seeing any of that out there. The data was taken by the WISE telescope, was pre the Kepler study, but there was none out there. So this paper then covered the various scenarios that it could be. Could it be the aftermath of a catastrophic collision in the asteroid belt? The problem is no infrared excess. We should be able to see that infrared excess in here, but maybe it just happened and we can't quite see the asteroid belt. And if we monitor this object later, maybe this infrared excess will show up. We want to look at that. Potentially a giant impact in the planetary system, like the one that formed our moon when we got hit by a Mars-sized object. These are usually indications of a young solar system. Every indication is this is not a young solar system, that it's an older star. So these things are not really, they don't fit very well. And then the dust-enshrouded planetesimals, the idea that you have something got hit and you got a small planet that has puffed up, has a little dust cloud around it. Another kind of similar thing would be planets with large rings that are actually doing this occulting. And the number one scenario is thought that maybe it's a family of comets that have come through here, potentially dragged out by an encounter of that other star that we saw close. They don't think that's a chance coincidence. They think that that star is indeed physically close to this system, either in orbit or maybe a star that is rogue star moving through the system that's dragged comets, that's caused a whole bunch of comets to fall toward this. So the idea is to see if there's some periodicity, or is this phenomenon going to actually go away over time. So they are looking now to see how this system is actually going to progress. Now, the last little thing that I wanted to mention about this story is it came out in September, and there wasn't much said about it until an article appeared in The Guardian this week that maybe it is actually alien megastructures that have been put up there. Okay. And, at first glance, this seems totally silly, but, it was, a credible astronomer who threw that out, because we have proposed for a long time that as civilizations evolve, they need to get more and more energy for these higher and higher civilizations. And one potential for getting more and more energy is to create these kind of what are referred to as Dyson spheres, named after Freeman Dyson, who proposed this back, I think, in the 60s, of building these structures around the sun so you could capture all the energy that is coming from the sun. So, yes, it could cause some of these weird effects. Very unlikely that it would, but I think it's those kind of things that we should think about sometimes, because it's been proposed because we are a civilization that's only been in this kind of technological era for 100 years or so. Imagine where we're going to be in a million or tens of millions of years. Will we be able to create things like this? I actually did a little calculation to say if we were going to build a shell around the sun at our particular orbit and use the Earth as the resource materials, how thin a shell would that be? Turns out it'd be only about 4 millimeters thick. So, but we just talked about there's 20 million Earth-like planets in this system. So this object now, SETI is actually pointing telescopes to it to see if there are any potential, alien signals that are coming from it. It's worth a shot. It's a very, all those scenarios that I told you are natural ones. Whatever it is, it's a very unlikely thing. There was only 1 in 150,000 stars in the Kepler field. And some of those scenarios are very unlikely things to actually have witnessed. So something weird is going on here, and it's going to be fun to actually get to the bottom of it.